All right, show us a demonstration.
The
Mhm.
collision.
Yeah. So this one's a little different because it's the similar setup to the last one, but the light car is coming in this time. Oh.
Sorry.
It's like all four efforts. Okay. All right, go ahead and show us what's up. So this time, the original car that was coming in hits and goes backward, yes?
Yeah.
All right, so tell us about the M delta V's for you guys.
Okay, so the initial velocity for car A, or the final velocity was negative 0.21, and the final velocity was the initial was 0.436, and the mass is 0.5, so the M delta V is -325. And then the final velocity for car B was 0.21, and the initial was 0, and the mass was 1.5 kilograms, and so the M delta V is positive 0.315.
So yours, one was positive, one was negative. One was 0.323, the other was 0.315. So here's the question, and we can debate it. Like, within our ability to measure with the computer, is it possible that this is like an actual thing here, that the change, the M delta V for one is equal but opposite to the M delta V for the other? Do you guys want to get on board with that? Like, how cool would that be if that were like the actual thing? Right? Okay? So I think that that's something that we should consider here moving forward, is like, is the M delta V for one equal but opposite to the M delta V for the other? Okay? All right, so leave your board. Let's come up to the front. Okay? Don't erase them because we're going to need to draw them again. But I want to draw something else here. Now, I want you to draw along with me. Okay? Yeah? Can you do it real fast? All right, so get out some stuff to draw with, get out some stuff to draw on. Did you have a whole conversation with yourself? All right. So here's the deal. Okay. So throughout all of our study, okay, what we've tried to do is we've tried to connect our understanding of ideas to pictures. And I don't mean like pictures, I mean like a pictographic representation. For example, okay? For example, if I drew this, what can you, if that represents an object, what can you tell me about that object? What do you mean?
The velocity was increasing.
Is it?
Or is it the same thing? I don't know. It looks like the arrows are getting weird. Or is it constant?
Well, within my ability to draw it, I try to draw them all the same size. Is this last one a little too long?
Yeah.
Sorry. Okay, how about now?
Okay, it looks the same. Yeah.
What does that say?
They're constant.
So this tells you, and I just drew some dots and some arrows, right? But you said, oh, I think that's an object that's moving at a constant speed to the right. I love that. What if I did this? What does that represent? So it's an object which moving which way? Down. And what's it true about its speed? It's increasing, and Noah said it's accelerating. Is that cool? Okay. What about this one? We'll put some words on this one. Okay, what are you seeing here? Is that better?
Yeah.
What do you notice about it? Forces are balanced. So tell me, give me a scenario that goes with this.
A ball on the table.
It's an object sitting on a table. Earth's pulling it down. The table's pushing it up, right? But again, this is just dot and arrow, right? So if we come over here and look at this one, this is actually a pretty complex representation, but still inside here we have these representations, right? We have two objects called A and B. B or A has kinetic energy before, after, they both have kinetic energy, and we lost some to thermal. So our ability to generate meaning with pictures really helps us understand something more deeply. Does that make sense? All right. So what we're going to do now is we're going to think about what's happening here. A crashes into B, correct? Is some of the energy transferred over? It is, right? But some of the energy is lost also. Okay? But what did we just notice back there? Is the M delta V for A equal but opposite of the M delta V for B? It is, right? So I wonder if we can, what if we calculate the MV for A before, and the MV for A after, and the MV for B before, and the MV for B after? Do you think there might be some deeper meaning there? Okay? So let's talk about this MV. If I take the mass of an object, and I multiply by the velocity, does that tell me something about an object? Think about a bowling ball. I'm going to roll a bowling ball at you. Okay? I'm just going to roll a bowling ball at you. If I roll it faster, is it more difficult or less difficult to bring to a stop if I move it faster? If I roll it faster? It's more difficult, right? So more velocity, which would mean it's harder to bring to a stop. Does that make sense? Now I'm going to think about a different bowling ball. What if I rolled one that was more massive at you, like a 12-pounder versus a 6-pounder? Which is harder to bring to a stop? Which is harder to bring to a stop? The 6, or same speed, 6 and 12. Which one's going to be harder to bring to a stop? The 12, right? Why? It's not because it's heavier. It's because it's more massive. That's right. Because what is mass? Mass is a measurement of an object's resistance to change in motion. True? So this MV, this is what we call the motion quantity. Okay? It's called the motion quantity. It's a measurement of how difficult it is to bring an object to a stop. Luke, are you with me back there? Luke! So much easier to bring this stuff into your brain if your eyes are open. Just a PSA.
I'm sorry.
It's all right, buddy. I'm not upset. I'm just worried for you. Because I want you to be able to, get this in a way that's meaningful. Okay? So this is the motion quantity. Now, here's the thing. Let me show you how we're going to represent this, because I love this idea. So it's mass times velocity, correct? So we're going to represent it as a rectangle, where the height of the rectangle is the mass, and the width of the rectangle is the velocity. Is that cool? So how am I going to calculate the motion quantity? What am I going to do? I'm going to take the mass times velocity. But isn't that just the base times the height? So what is that?
That's the area of the rectangle.
It is the area of the rectangle. That is correct. So far, so good? All right, now how are we going to transition to our whiteboards? Great question, Don. How are we going to? So we're going to include, so we have the before picture and the after picture. We got the before bar, the after bar, and the system, correct? We're going to draw a new representation here. And it looks like this. There's going to be before and an after. Where the vertical is going to represent the mass. And the horizontal is the velocity. How's that look? Okay, give me a second to catch up. So let me put some numbers on here so that we can get this. This is a ½ kilogram. Still a ½ kilogram. Okay. And let's say it's moving to the right at 0.6 meters per second. Okay? This guy's a 1 kilogram. He's at rest. And afterward, I measured their speed at 0.2 meters per second. Is that cool? All right, so this is how this diagram works out. What is the mass of the green guy? It's 0.5, right? So I'm going to draw it right on this axis right here. .5. And this is the velocity. What's the velocity? 0.6? How's that look? Amazing. What about this other guy? What's his mass? It's 1. So when I go to draw his mass on this axis here, how much longer is it going to be than the green one? Twice as long. That is correct. Who said twice? Love it. What's his velocity? What's his velocity? 0. So he doesn't get any width at all because he's not moving. Now what's happening over here? I have the same masses. But what's the speed of these guys? It's only 0.2, correct? That's a third of this. So when I draw it, oh no. Alright, we're going to have to pick it up when we come back tomorrow. We are going to assess tomorrow also, so if you haven't assessed on B's or C's, tomorrow's your day.